Hi everybody, welcome to your second video here, getting ready for AP Calculus AB. Thanks for hanging in and putting in this time over the summer. I really do think it'll make the start of calculus a lot smoother for all of us. So in this video, we're going to talk about graphing piecewise functions. Instead of using tables this time, we really want to focus on using known parent functions. So the functions we're going to talk about on this first page are really ones that we all need to know. So if we said y equals x squared, we should all have a picture of what that looks like. And that goes for everything on this page. So the first thing I want to do is just kind of quickly run through what all these graphs look like, and then we'll use them to actually graph some piecewise functions at the end of the video. So, y equals x, hopefully this is an easy one for us to all remember. We know this is a line, right? It follows that format, y equals mx plus b. So in this case, our slope is 1 and our y-intercept is 0. So it starts here, and then it just has a rise over run of 1 over 1. So it kind of cuts diagonally through our coordinate plane here. Ideally, I should be using a straight edge. I apologize that I don't have one with me. Okay, so there's our graph of y equals x. Now, for y equals the absolute value of x, it's actually pretty similar to what we did with y equals x. So for my positive x values, it's going to look exactly the same. Now, down here, absolute value takes those negative values and makes them positive. So this is just going to pop up here on the other side. Okay, now y equals x squared, we know that's a parabola. It has its vertex at the origin here. So if we just do some values, I know 1 squared is 1, 2 squared is 4, and then pretty quickly we're going to go off of, oh, that's not right. 1, 2, 3, sorry about that, 4. And I know it's symmetric there about the y-axis. So it's going to look like this. Okay, now x cubed, I know I've got 1, 1, actually 2, 8 is going to go kind of off the page here. And so x cubed, what it looks like is something like this. Now, we also could look at the cube root of x. We have these same kind of points here as our anchor points, but now our graph is going to look like this. There's our cube root of x. For 1 over x, we're going to have a couple asymptotes here. Obviously, x can't be equal to 0, so we know we have a vertical asymptote here. And because we're bottom heavy here, we're going to have a horizontal asymptote also. Now, for key points, I can look at when x is 1, I know y is going to be 1. When x is negative 1, I'm going to have y is negative 1. And then it just looks like this, kind of approaching those asymptotes. Now, for y equals 1 over x squared, we have a similar situation here with our asymptotes. But now my points are a little different. If I plug in a positive 1, I'm still going to get 1. If I plug in a negative 1, that square is going to make it positive, so we have a positive 1. So now this piece is going to look the same, but what was below the x-axis here, is just going to come above. Okay, now for the natural log of x, we know that a key point to remember here is going to be the point 1, 0. And so here's something to remember. Natural log, hopefully we all remember that natural log has a base of e. So if we're saying 1 is equal to the natural log, that's base e, or our y is 0, our x is 1. If you think about those log circles, we know that e to the 0 is equal to 1. So that's why our point 1, 0 lies on this graph, and then it's going to go like this. Again, for this graph, I'm just concerned with you having that one anchor point, and we don't really worry. I just want the general shape for that graph. Now, for e to the x, I know that e to the 0 is equal to 1, so I'm going to have the point 0, 1 on this graph. And then it looks like this. Again, I'm more concerned about the shape and having that one anchor point. Okay, square root of x. We have the point 0, 0. If I plug in 1, the square root of 1 is 1. 4, square root of 4 is 2. And so we have this shape. Square root of 1 minus x squared, that's going to give us a semicircle with radius of 1, centered at the origin. So that is going to look like this. In general, what we have is y equals the square root of r squared minus x squared, where r is the radius. So in this case, the square root of 1 was 1, and that's how I knew there was a radius of 1. Okay, now for sine. I know that sine of 0 is going to be 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And so then I can just keep going with this pattern. And I can follow it this way as well. So there's our sine, something we will be working with a lot. All right, a few more. Okay, cosine now, very similar to sine, obviously, but now our cosine of 0 is going to give us 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. 3 pi over 2 is 0, and again, we can just follow that pattern. Now, for tangent, we have to be careful here. We know that tangent is equal to the sine of x over the cosine of x. So obviously, we're going to have some vertical asymptotes wherever cosine of x is equal to 0. And we know that happens at the multiples of pi over 2. So I'm going to sketch in. So I have pi over 2. Pi is going to be okay. At 3 pi over 2, we have that. So then we're going to have, again, asymptotes at negative pi over 2 here and negative 3 pi over 2. Now, in between those intervals, we're going to have intercepts here. So in other words, sine of 0 is going to give me 0. Cosine of 0 is 1, so 0 over 1 is going to give me 0. Same thing happens at pi. Sine of pi is 0. Cosine of pi is negative 1, so we're going to have 0. So we have zeros, and then it's just trapped in between those asymptotes. Have like this. There's our tangent, and then inverse tangent is similar, except it has some horizontal asymptotes. And so it's going to look like this. All right, so those are the parent functions now that we'll be using, and we'll use these really all throughout calculus. Knowing these parent functions and some basic transformations is going to make a lot of the work that we do throughout the year a lot easier. So let's see how this might help us when we're graphing piecewise functions. Now, the first one we have is a pretty straightforward function. I can see that I basically just have two constant functions. So it means when I graph these, I'm just going to have horizontal lines, as these are both just constant. Now again, if it helps, I know I have a breaking point when x is 0, and that might be hard to see there because I'm right along the axis. I know that's probably not much help, but that's where my two functions should kind of break. So for my first one, I have -1 when x is less than 0. So at 0, I know I'm going to have an open circle at -1. And no matter what x is for less than 0, my function value is always going to be -1. So I'm going to have a horizontal line. Now, when x is greater than 0, I have a +1. Again, I'm open because I'm strictly greater than, but again, no matter what value I have that's greater than 0, I know my function value is going to be a +1. So that one was pretty straightforward. For our next one, we're going to have two different parts here. I know my first part is going to be a line. And now I have my breaking point here is at -1. So I know this is a line with a slope of 1 and a y-intercept of -2. Now, in my head, I'm kind of doing what I would do with a table. Beyond knowing what it looks like, I'm just going to kind of test some points. So at -1, if I subtract 2, I have a -3. And I know that's going to be closed. Now, once I have that point, I know this has a slope of 1. So to make that positive, I can go down 1 and left 1 to get some more points. And that gives me my linear piece. Now, for my second one, I know I have a parabola, and I have a pretty good idea of what that looks like. So at -1, I'm going to have a +1 for my y value. This is going to be an open circle because it's strictly greater than. And then I know what those other points on my parabola are going to look like. So I don't have to do that table anymore because I have a good picture in my head of what that should look like. And again, I've been forgetting to do this, but we can get rid of this here. That was just to kind of help us remember where our pieces should break. All right, for my next one, there is a little bit of a typo here. If you notice the breaking point for sine, this is for x less than or equal to -π/2. So this should be x greater than π/2. Or -π/2, excuse me. Wrote it right and said it wrong. So -π/2 is where I'm going to shade in for my breaking point here. So for less than -π/2, I have my sine curve. Now this is less than or equal to, so it's going to be closed. So sine of -π/2 I know is -1. And so I'm going to the left here. Sine of -π is going to give me 0. Sine of -3π/2 is going to give me a +1. And then I'm back to 0. So there's my sine curve. Now for tangent, remember we have those asymptotes. So I actually do have an asymptote for my tangent function. It's okay for my sine function to touch because that doesn't apply there, but I know I need that for my tangent. And so in between I have my zeros, and there's my tangent function. So again, knowing those parent functions just saves me time because I don't have to think about plotting a lot of points or making a table. I just know what that shape should look like. Yes, I can draw in one more here. All right, let's see. We've got one left. This one, again, has 3 different pieces. And so we'll just use the same ideas just to reinforce this kind of graphing piecewise functions. And hopefully if you have struggled with this before, it's becoming a little more clear now that we've gone through some examples. So what I'm noticing right away is I have a breakpoint at 1. So I'm just going to sketch that in. Help me keep organized. And then at 3 as well.